Okay, so yeah, it's a great pleasure to have Igor Shovkovy with us. So he has been thinking about chiral symmetry and anomaly and its effect from cosmos to the condensed matter systems. And he has been working on so many exciting topics. And today he will be telling us about riding the wave of relativistic-like hydrodynamics. So Igor, please go ahead.
Okay, well, thank you very much. Thank you for the invitation to give this talk. I'm very glad to talk about this topics we were recently working on. So I do also have a small introduction, and because of the previous speaker who actually introduced many of those things, I might go a little bit quicker through that. So actually it helps. But I would still want to give you a little bit of that introduction so that it's giving a slightly different perspective on the same ideas. So as we heard from the previous talk also, the actual band structure of the materials are very complicated usually. So one of the sketches of those band structures I'm showing on the right-hand side for some specific material, it's actually not measured, it's calculated. But it doesn't really matter. What really matters is the complexity of that band structure. As you could see, there are a lot of different structures that seem rather involved. And you might wonder what kind of general things could happen there. And in fact, there could be a lot of interesting surprises that happen. One of those is actually the possibility of creating those so-called Weil or Dirac nodes shown in this particular material in one space of the Brillouin zone where you have that separation. So one of the natural questions, if you are a theorist, would be to ask, well, how likely or common those are in general? Because we were studying materials for hundreds of years, really. We know the band structures for at least 50 to 70 years, many of those maybe longer. And actually, it's only like 7 years ago or so that we started to talk about this Weil node. So it's very, very natural to ask how common they are and when they appear. Well, first of all, what's the origin? The origin really is the energy level crossing. So generically, you have all of those band structures, and in some cases, they may cross. At the point of the crossing, if you are looking at quantum mechanics and you remember the degenerate perturbation theory, you might ask, well, those kind of things, they're kind of tricky because of the levels that they could that could repel. So then you might ask, are they really crossing with the gapless node at the point, or they are repelling each other and you are creating a gap? So that's something that you really have to ask yourself. Well, the generic two-band Hamiltonian can be written very easily. And notice, I'm not using any spin degrees of freedom here. I'm using the band degrees of freedom. But essentially, it's a two-dimensional space because we have two bands generically crossing. So when I'm considering that two-band crossing, I could parameterize that with a 2x2 matrix, or if you wish, I could use this Pauli matrices to parameterize the most general structure of the Hamiltonian. The corresponding energy near the band crossings, or near those points where they're supposed to cross, will look as follows. And the condition that the bands actually cross, so there is no gap, means that the B coefficient has to be 0. That's exactly what is the splitting would be. Now, in 3 dimensions, this is 3 equations because B is a vector quantity. And of course, since you have 3 different momenta or quasi-momenta in the Brillouin zone, you could always solve for the values of the 3 values of the components of the momentum and find when that equation is satisfied. So actually, this appears to be always possible, at least in some parts of the Brillouin zone. So actually, that gives us a very simple conclusion that the band crossings of this type are not unusual. In fact, they are very common. Moreover, if you think about it, many materials do have it. Even something as simple as iron has those crossings. The only tricky thing that is important, and it became extremely important in the last 7 to 8 years, is actually that sometimes those band crossings could happen near the Fermi surface, and that's when it becomes really interesting. Anyway, Leaving that aside for a moment, let us look what happens near those band crossings. So if you're going to consider small deviations of momentum from the point where they cross, you could write generically the expansion of the Hamiltonian as follows, basically nothing else but the Taylor expansion. For a moment, I will neglect this second term. This scalar term is essentially giving you something called the tilt of the cone of the node. And essentially, if I straighten it up, that's basically what means neglecting that term. Of course, in reality, it's never really zero, but for a second, it's okay to neglect it. After an orthogonal transformation in the second term, so basically changing the coordinate system, you could always diagonalize the matrix Bij, which is nothing else but the derivatives with respect to momentum, and you could write the Hamiltonian in this standard form, where in principle, I'm assuming that the velocities in different normal directions are not the same. When isotropy is assumed and when you choose the reference point for the energy at the node, then you will see that we will derive this conventional, simplest possible wild Hamiltonian that we often analyze in models. So of course, the simple lesson is that first of all, those nodes are not rare. Secondly, they are slightly more complicated in reality. They have tilts, they may not be exactly isotropic, but also you could realize that in all of those possible cases, you could still define a well-defined chirality. And that is given by essentially the determinant, the sign of the determinant of this matrix. So that's the first thing that I wanted to say. The second thing is topology. Again, the previous speaker already briefly discussed that. So let me just give you a few sketches that will tell you a little bit more precisely where the topology is hidden. So solving this Hamiltonian, you could find the eigenfunctions, eigenvalues, they are listed here. Technicalities are not that important. I just wanted to make sure that this is very, very specific and the student could just sit and repeat that in 5 minutes. Now, when you consider those wave functions with those energies, you could realize that there is something very interesting about the mapping of the wave vector to the wave function. So this function from K to the wave function is actually having non-trivial topology. How do you see that topology? Well, one way to see it is to have something like adiabatic evolution of the wave function. Think, for example, of this wave function that will be slightly modified where you apply arbitrarily weak magnetic field in space. When you have arbitrarily weak magnetic field applied to the system, the particle will start to change its momentum. It will start, the trajectory will start curving slightly. So you could analyze that adiabatically by using the evolution of this wave function, and you could see that you could parameterize that evolution by the so-called Berry curvature that is defined through the wave function. So take the gradient, take the, or if you wish, take the ground state expectation value or the wave function expectation value of the gradient in momentum space, and you will find what that Berry curvature is. Of course, there is a subtlety here. The wave function is not uniquely defined. You could define it up to a phase. This can change. So there are a lot of things that might sound very similar to the gauge symmetry if you were working in the coordinate space. Now, those ambiguities, they all will go away, and that phase will be completely irrelevant if you define the so-called Berry curvature. And I did calculate it from the Berry connection in the previous slide, and you could find this result very easily. In momentum space, it has a very traditional form. It's actually nothing else but a monopole. If this were an electric field in coordinate space, you would say that this is essentially like a Gauss law. If this were a magnetic field in coordinate space, not momentum space, you would say that is a magnetic monopole. Anyway, why do we call that a monopole? Well, because you could calculate the corresponding charge by surrounding the curvature or this quantity omega with a closed surface and integrating over that closed surface, and you will find that the result is proportional to the sign that appears in front of this Berry curvature. This Chern number is essentially the same exact thing as the chirality defined in the previous slide, because if you trace the origin of that back, it just defines the sign in front of the sigma k term in the Lagrangian, or in the Hamiltonian, I should say. Now, also in the previous talk, you heard briefly about the Nielsen-Minomial theorem. So let me also give my way of thinking about it. If you have those very monopoles in the momentum space, then you have to analyze what exactly is happening if you have a compact Brillouin zone. In solid state materials, the Brillouin zones are not infinite space. They are actually compact spaces. And if you think of this blue box, you just have to repeat it periodically in every direction. Now, imagine that you are doing the same exercise in this Brillouin zone, and you picked one of your monopoles here or there, and surround that with a closed surface. By the way, this yellow thing is a closed surface because it's a compact Brillouin zone. So if you consider enclosing the top monopole and doing the integration, you will find that the sign is negative because the lines are going inside the surface. But when you're considering exactly the same surface from the other direction, this is an oriented surface. From the other direction, it will look as a surface surrounding the other region of the compact space. And basically, in that case, the integral is going to be positive. The sign will be positive. That basically means that if you have a negative monopole here, it will be a positive monopole down there. So that's essentially the essence of the Nielsen-Minomial theorem, and it basically tells you that the net topological charge has to be 0. So that's essentially the origin of that statement, that the nodes have to come in chiralities of opposite sign. Very naively, from the point of view of, if you wish, high energy physicist, if you consider the Hamiltonian for the corresponding models, you could define the Dirac Hamiltonian in the usual way. And by the way, I'm considering now the Dirac Hamiltonian in a sense combining two nodes in the same Brillouin zone. But if they are sitting at the same position, so basically the charges are canceling each other, you would have nothing else but the standard Dirac Hamiltonian. You could split those nodes by introducing two different types of terms of this type. One of them is the so-called chiral shift. It shifts the nodes horizontally in momentum space. The other one is V0, which is the time component of this chiral shift, and it shifts the nodes in a vertical direction. They come with the symmetry breakings. The first one is breaking the time reversal symmetry. The other one is the parity symmetry. So basically, as soon as you introduce those, you have to be aware of the fact that those symmetries might be broken. Actually, I should probably make a side remark that not all wild Dirac metals have broken time symmetry. The reason is that typically you get many different nodes, and sometimes they come in parallel pairs, if you wish, where the time inversion symmetry is restored if you go from one pair of the wild nodes to the other. So actually, not all wild materials have to be magnetic, for example, to break the time reversal symmetry. It's actually a very important subtle issue that sometimes is ignored. So that was my very, very brief introduction to give you the connection to the topology at the most fundamental level. But the actual topic of my talk is really about the electron hydrodynamics. So before I go deeply into that, let me give you again a very, very brief introduction of what that means. Well, in simple terms, electron hydrodynamics means simply that the electrons inside of the material, inside of your semi-metal or metal, they behave like a liquid, correlated liquid. So essentially what that means is the interaction between the electrons themselves is happening so rapidly on such short time scales, LEE, that essentially all other interactions, for example, with those impurities sitting somewhere will be happening very rarely. Also, perhaps very rarely, the interactions will happen with the walls of this channel in the case when we achieve the hydrodynamics. So what's so special about this regime? Well, this is the regime when the electrons scatter on each other as rapidly as they want. But the thing is, since they are part of the same liquid, they are essentially conserving the total momentum of the liquid that is moving. Only when they're scattering on the impurities that are basically stuck somewhere in the channel, that's where they start to lose that momentum. So those are typically called momentum changing or momentum relaxing collisions, and the corresponding characteristic length is L sub p. So when L sub p is much larger than LEE, you generically may have this possibility of the hydrodynamics of the electrons. In the case when the temperature is extremely low, however, both of these landscapes become very large, and if you have a finite length of the channel, they may not be exactly achieving a nice hydrodynamic regime. You would have something that is more like a ballistic regime. So that's essentially the curve that I took from the original paper of Radi Gurji, who originally proposed the idea. Now, when the electron-electron interactions becomes the most common interaction, essentially the corresponding length scale is the shortest in the system, that's where you could get this unusual behavior. And unfortunately, because of the time constraint, I will not be able to explain all of these subtleties in detail, but this is called the Gurji effect when you enter this hydrodynamic regime first through this regime where the hierarchy of scales is given in green, and then the hierarchy of scales, which is given in purple. Then basically all of this will be the hydrodynamic regime before you enter the standard metallic regime at the end of this curve at higher temperatures. And observing something like this is the characteristic feature of reaching the electron hydrodynamics. Now, this electron hydrodynamics has been observed in some materials, in two-dimensional materials. I should actually mention that the first observation date back to 1990s. These are more modern experiments done in graphene, and that basically, again, without going into all the details, they're basically showing you that in some certain geometries, you could have a very unusual transport. So this is called higher than ballistic transport. If you have a constriction in the material, think of this as a graphene with a little two pieces of the graphene disconnected in this region and only connected in one of these regions where the white color is, then you will find that the transport, the actual resistivity drops below the so-called maximal possible ballistic transport, which is shown in the black lines. And theoretical ideas are explained in this PNAS paper, and the experiment is given in this Nature Physics paper. There were some other indications of the hydrodynamic regime in electron hydrodynamics in these papers listed here. So you could also consider some special geometries where the non-local resistance will be negative. So essentially because of the drag in the flow of the liquid, you will see that in some parts on the same side of the channel as the, let's say, positive contact is, you may have a negative potential induced, and that formally will indicate something like a non-local negative resistance. You could also visualize the porosol flow in the system, and again see that it looks more like that picture I showed on the previous slide, where the profile is parabolic. So all of those are the indications of the hydrodynamics in two-dimensional systems. There are also first indications that the hydrodynamic regime may be achieved in wild semi-metals in 3D. This is one of the experiments. Actually, there are two experiments reported here. And one of the features of the first result is given in this slide, where the dependence of the resistivity on the width of the channel, you see there are different widths of the channel. And when you consider how the dependence happens on the width of the channel, the exponent -2 will indicate a parabolic shape. So perhaps I didn't emphasize it here. It's this dependence that I was showing on the general Hydra slide. And that is exactly the same, potentially the same dependence that is happening here. Of course, there are some critical remarks about this work, and perhaps it's not completely 100% settled if it's true, but there are at least indications. Anyway, I'll take that as a given and essentially try to see what could be the potential implications of the relativistic-like hydrodynamics for the electron fluid in those Dirac and Weil materials. So before I go there, I don't have my time on me. Just a second, let me check. Okay, good. Just want to make sure I have enough time. So when you're talking about the hydrodynamics, the first thing you have to understand what exactly is hydrodynamics. Well, hydrodynamics is the evolution of the system on very long distances and long time scales. On such large distances, typically all the microscopic processes that are happening in the system are becoming pretty much irrelevant. As soon as there are rapid enough interactions in the system, as soon as the system is locally in equilibrium, and I emphasize locally in equilibrium, it basically means that the system is pretty much in a boring equilibrium state everywhere locally. However, on very long distance scales and long time scales, you may see that there are some inhomogeneities in the system. So how do they evolve? Well, they can all really evolve according to the conservation of the laws. That's essentially the only things that are left that could still evolve slowly. And slowly, essentially, because we are considering the only weak long scale perturbations. All of those quantities, of course, are conserved. The energy is conserved, the density is conserved, the charge is conserved, and basically for all of those quantities, we know how to write the corresponding conservation equation or continuity equations, and they will be the equations for the conservation of the momentum, energy, and charge. And even though this looks a little bit unfamiliar, this is nothing else by hydrodynamics. The first one is the essentially Navier-Stokes equation. The second one is the energy balance in the system. And finally, the last one here is the conservation of the charge in the system, be it fermion number, electric charge, or whatever else is conserved. Of course, here there might be also external forces applied to the system, some electrical fields, as we typically like to do in electronic systems, maybe some magnetic fields, as discussed in the previous talk. And there could be also some other forces acting in the system, for example, due to impurities. Anyway, everything is standard. You could write it in terms of the general quantities that appear in these equations. However, we're dealing with the Weil semimetals or Dirac semimetals, and there could be some subtleties. One of the subtleties is the chirality. As I discussed, there could be a well-defined chirality of the quasi-particles near the nodes. And of course, that you could describe with the corresponding conserved charge. Well, I should say approximately conserved chiral charge. That chiral charge is only approximately conserved because of the chirality. So this is the standard and the chiral anomaly E dot B term. And of course, because in principle, it's not as exactly conserved as the regular charge, because in principle, you could have the transitions, for example, unclop processes that will turn left-handed into right-handed particles. So there will be some lifetime of those charges. Typically, that might be considered a very small gamma 5 or very small rate of transitions. And in that case, this is a good equation. When gamma 5 becomes large, this becomes essentially irrelevant. Finally, we are dealing with the electrons, and electrons are charged. So in principle, as soon as you start messing up with the electromagnetic fields applying to the system, you absolutely must include Maxwell equations in the discussion of the system. So basically, that's the complete system equation. Of course, I assume that everybody knows how the Maxwell equations look like, so I'm not writing them explicitly here. Now, those equations, they are not self-contained unless you are actually going to specify the expressions for the currents and energy density tensor in terms of the corresponding dynamical parameters. If you introduce, for example, the flow velocity V, charge density, energy or temperature and chemical potential, then you have to actually write all of those quantities. There are a lot of them, but they are written in relatively few independent quantities, and those relations are called constitutive relations. So here there are several standard expressions. For example, in the current, there is current density times velocity. There are some dissipative terms that includes all kinds of conductivities, heat, electrical conductivity, and all kind of that stuff. But I added a few new terms here that I want to specify explicitly, leaving everything else outside. There are also anomalous currents and anomalous current densities that are appearing because of the chiral anomaly, because of the chiral nature of quasi particles. And they include many different interesting effects, something that is called like chiral magnetic effect, when the current is induced by the presence of the magnetic field and the parity violating medium, or something similar due to the vorticity of the liquid. You could also induce axial or the chiral currents in a similar fashion. And all of those transport coefficients, they actually non-dissipative and they are anomalous. And those non-dissipative anomalous coefficients can be calculated when you know, for example, the chemical potentials in current chemical potentials and temperature in the system. There are also two red terms, which are Chern-Simons term, and I'll explain them in a second, because that's something else that appearing in condensed matter materials, which may not be so easily visible in high energy physics, for example. Now, when you write those expressions explicitly, of course, the corresponding Euler equation or Navier-Stokes equation will be very complicated. So basically, I only wrote a couple of terms and left everything else outside. It will be several pages if I use the slide presentation like this. And something similar for the energy conservation. So that's the first two equations. Then there is the Maxwell equation, and there are those two additional continuity equations. So all of that can be written down explicitly. And again, it's not the technical talk to give them here, but I do want to make sure that you've seen at least once some snippets of those Chern-Simons currents that appear in the discussion in the equations. And those Chern-Simons expressions, for example, for the current for the charge density and current, will have the following form. Notice that they are given via the chiral separation parameter B and B0 that appear in these expressions explicitly. Also, this last term is nothing else but the so-called chiral anomalous Hall effect, when you have the current induced perpendicularly to the electric field. Briefly about the origin of these terms, they come actually in a topological manner. They are coming from the fact that when you are considering the change of the chirality on the left node, there will be some change of the chirality on the right node because they are intimately connected to each other via the bottom of the filled Dirac band. So essentially the lower band, the valence band, if you wish, in terms of condensed matter physics, when you are going to consider pushing the chiral fermions on the left-hand side downwards, they will appear on the right-hand side upwards. And that's essentially how the topology works here. So in a way, you might say that they are not decoupled from the ultraviolet physics, which is happening on large energies at the bottom of the band. And they can be formally derived very easily. Anyway, those are the general sketch, that is the general sketch of the formalisms that we are using. And now I'm coming to the actual predictions that might be very important to understand what's so special about this regime of chiral hydrodynamics. So I'll give you three very brief ideas where the chiral hydrodynamics plays a role and affects observable properties. So the first sketch is the collective modes. So as I said, hydrodynamics is dealing with the excitations on long wavelength and long times. And in this case, you could consider the weak perturbations of the system. When you take your system slightly out of equilibrium, I could parameterize that, for example, with the chemical potentials, temperatures, and velocity that are slightly away from equilibrium value, and consider the solutions for the equations in the form of plane waves. So essentially, I'm assuming that the amplitudes are arbitrarily weak. And in that case, I can have essentially a linearized equation, a set of equations that I could solve. So in this case, I could consider all the equations. And of course, I'm not going to overwhelm you with those equations, but I'll have to tell you that the most unusual part, the most characteristic things in this hydrodynamics will be actually inside of the current and current densities, charge densities and current densities, which will have a lot of those anomalous terms. There will be all kinds of chiral magnetic effect, chiral separation effect, anomalous Hall effect, and all of that is captured pretty much in all of these terms that are shown here. So again, you don't have to bother to look into all the details, but you could see at least some snippets of them. For example, this term in the middle is the anomalous Hall effect, where you have the current induced perpendicularly to the electric field. And if you study this system carefully, you will find a very rich spectrum of collective modes. You could analyze many of them. And just to give you an idea how this may work, I'm just showing you only one specific mode of one specific type of wave, anomalous Hall wave. Longitudinal means that it's propagating along the direction of the magnetic field, and the corresponding chiral shift is perpendicularly to that direction. This is the spectrum. Again, there is nothing super important about this, perhaps only one thing, that this is a gapless mode. This is a gapless mode proportional to the momentum with some characteristic velocity given by this expression that depends on magnetic field temperature and all of that. Now, why this is interesting? Well, first of all, because it cannot exist in regular hydrodynamics. It cannot exist in a normal system because it heavily relies on the chirality and heavily relies on anomalous Hall effect. So the continuity equation for the charge, for example, tells you when you change the chemical potential, you will induce non-zero chiral chemical potential. The presence of those two from the other continuity equation and the anomaly tells you that you will necessarily use the electrical field component parallel to the same direction of the momentum and magnetic field. With that component of magnetic field, you will see, electric field, you will see that the perpendicular component of the electric field must be induced from the Maxwell equations, and this will be perpendicular to both of those directions. And then if you consider yet another Maxwell equation, for the electrical field, you will see that you are closing the system equations and you have essentially all of those four quantities appearing and giving you a non-trivial solution. So basically, this is a closed system of the equation that gives you that collective mode. Of course, in many cases, there are more independent equations and the solutions are much more complicated. But this is just to give you the idea that there are certain types of modes that are only possible in the presence of the chirality present in the system and in the presence of the anomalous Hall effect. And this is the new type of collective modes that you could observe. Another?
Hi, Igor. Igor, can I ask you a question?
Yeah, sure.
What ensures this chirality or N5 is a slowly varying quantity in these systems?
N5 itself is 0. Mu5 is non-zero. So essentially, when you have the regular charge, it's present and essentially it's large. N5 is absent. But delta mu5 is the oscillating representing oscillating charge in the system. So mu5, N5 itself is 0, the background value in equilibrium. Around the equilibrium, when we deviate the system, there is a non-zero N5 proportional to mu5. Does that answer the question?
Yeah, I know. I also wanted to ask you, why is it slowly varying quantity? What ensures that hydrodynamics is valid for it?
Exactly, because I'm considering the hydrodynamics. This is essentially the scheme that is valid only when everything is happening slowly and on large distance scales. That's the only regime when hydrodynamics is truly applicable. By the way, the same modes, if that's the insinuation of the question, the same modes or similar modes can be considered outside of that regime where the oscillations are happening or a little faster, or much faster, in fact, and on much shorter distance scales by using the chiral kinetic theory, which has also been analyzed, but I'm not reporting it here in this talk.
Thanks. Yeah.
So the other thing that I want to discuss is actually, and it's also kind of the spirit of my talk, the thing is that this chiral hydrodynamics have been observed in 2 dimensions, but in 3 dimensions, it's still a valid hypothesis, but frankly, not exactly an established fact. So in fact, what we are trying to do in our work is trying to find some characteristic features that will indicate that we did achieve this regime in nature. So one of the things that you might ask, well, if this is hydrodynamics, then perhaps there will be the most characteristic feature of a hydrodynamics convection. So why don't we look if a convection is possible in the system? And then if we see something like that, if you drink coffee in the morning, as I just did, you might see those little cells that form at the top of the surface. And essentially, they're representing the convection that is happening, like in this picture, when the flow is going from the bottom up in a convection way, in a convective way. So let's analyze the problem of a possible convection in this electron hydrodynamics. Well, before I go there, I might also want to mention that this kind of regime will be extremely useful for applications because, in fact, convective flow could be extremely useful for efficient heat transfer. And if you have that regime achieved, for example, in a material on top of your motherboard or a processor in your computer, then basically you could cool it down very efficiently, maybe 100,000 times faster than usually if you have only diffusive heat transfer. One of the things that characterizes the material and the situation that drives the convection is the so-called Rayleigh number. That's essentially the ratio of the time scale for the diffusion and the convection in the system. So if you consider copper as the thermal conductivity, you will see that it helps the heat transfer, and therefore it actually works against convection because it doesn't help driving the actual flow of the liquid. The heat transfer is efficient enough by itself, and then basically it suppresses the convection. The other characteristic is the convection time, essentially under a given force. So G here is the gravitational constant in the usual context. And of course, the characteristics that is appearing here that is very important is the viscous drag, the viscosity. So if there is, again, large viscosity, it will prevent the convection. It will slow the convection. So basically, these are the players in the game. Heat conductivity, viscosity, and the driving force. Notice that there is also very non-trivial dependence on the size of the system. For large systems, it will be easy to achieve. For small systems, it will be hard to achieve convection. So in the case of electron hydrodynamics in Dirac-Wilson and metals, you could analyze the equations. So essentially, I wrote again the equations. You could ignore them. Essentially, what I'm doing is the following thing. I'm doing the analysis in 2 steps. I'm considering what is the pre-convection steady state. So essentially, when I'm increasing the driving force, you will have the gradient of the temperature and the driving force. By the way, the driving force for electron hydrodynamics is not gravity, but much more efficiently electrical field, represented by this potential phi tilde. Tilde means in the steady state regime. And of course, before the convection happens, so before the threshold reached for the convection, you will have some steady state. So we found that steady state, and then we try to analyze again using linear approximation, the appearance of the instability in the system. Notice that the screening effects will play an extremely role in this description, and that's why I'm using this last Gauss equation as one of the equations that are important for the description. Oh, and by the way, also notice that this is important for screening the external field, partially at least. And this is going to be also very important for the convection itself. If you remember how their usual convection happens, of course, it's due to the decompressions of the fluid that becomes lighter, heavier in the field that is present, in the field of the electrical field in our case, not the gravity, but nevertheless, the idea is the same. And those compressions, decompressions, they actually also induce an electrical field, because the compression of the electron fluid with respect to the lattice is not affecting lattice in any way. The lattice of the ions remains in its own place where it used to be, and essentially that means that you create a compressed liquid which is partially charged, and where the Coulomb forces, the screening Coulomb forces, will play an important role. So all of that is taken carefully into account, and when solving the equations with the non-zero fluid velocity, and that velocity is arbitrarily small at the point of the instability onset. So those quantities with sub-u parameter, they will be essentially, again, in the form of plane waves. You substitute in the equations and find that the characteristic equation when the solution exists is given by this formula. The left-hand side is the Rayleigh number in the system at hand. So essentially it has the driving force, dependence on the size of the system, the conductivity, the viscosity. By the way, conductivity, not heat conductivity, but electrical conductivity here, but essentially they are related, so it's not that big of a difference. What is important that this non-trivial solution is not always present. In fact, if you look at the right-hand side, you will see that that quantity is bound from below. It cannot be smaller than a certain number. In fact, you could estimate what that minimal number is by trying to minimize as much as possible. Notice you cannot take a perp goes to 0 because this will become infinity. But you can take a x going to 0. This will be definitely decreased. But then if you try to minimize with respect to the remaining k perp, you will see that there is a certain minimal value you have to reach. If that is not reached, you cannot satisfy this equation, and basically you cannot have convection. And it's very important. There are several notations here. One of them is representing essentially the Thomas Fermi momentum. If you wish, the screening effects are encoded there. And the other one is the Gorgie length, which is encoding essentially the effect of impurities. Now, to analyze what is happening in the system, as I said, it's useful to consider what is the minimal value. If those quantities, there are no impurities, there is no screening, the minimal value for the kx is determined by the size of the system. Essentially, you will find that the minimal Rayleigh number needed in the system is something on the order of 650. It's a pretty large number, but that's essentially what is the quantity appearing in normal neutral fluids, and that's essentially the number you have to reach before the convection starts. When you have a finite lambda, so you have some impurities in the system, and you have non-zero chemical potential, so the screening in the system, then you will see that that minimum number is larger than this quantity. So you have to reach at least this number. Realistically, it have to be even larger than that. And that's the minimum number you have to achieve. If you estimate what is realistically achievable, it's something given by this formula. So I substituted the parameters, typical parameters for the Dirac-Weil semi-metals, and I could compare the two. So what is needed is the solid lines at the top. What is realistically achievable is in the corner on the right. So as you could see, and this is logarithmic scale, we are very, very far from reaching that criterion of convection. The reason is the screening effects and partially the impurities. If there are no impurities, this formula changes, but you could still find that essentially somewhere there, that those are absolutely unachievable. In fact, even when the screening is relatively weak, as weak as I could imagine potentially in realistic materials, and this is already pretty much unrealistic, even in that case, you have orders of magnitude to reach that criterion. The physics behind this is very simple. Those compressions and decompressions of electron fluid that are needed for the convection, they are basically screened out very, very efficiently by the Coulomb law. by essentially the Gauss law. And as a result, you cannot compress, decompress, and therefore you cannot achieve convection. That's it. That's essentially the idea. So unfortunately, one of these characteristic phenomena that you would naively assume would be possible is impossible in electron hydrodynamics. In graphene, the situation may be a tiny bit better because you have the screening that is not total, because graphene is a two-dimensional system. Electrical field lines, they escape in the third dimension. So in that case, you could have some like gradual channel approximation. Instead of the Gauss's law, you would find a different equation. You have some parametric suppression of the Rayleigh number due to the screening effects. So it's not as bad. But in fact, because of realistic values for the impurities, you still find that you need extremely large samples of super clean graphene before that convection will be possible. So even in graphene, which is a little more realistic, even in that case, pretty much it's impossible. So that's the story about the convection. So two stories: collective modes, convection. The last one is a new type of wave instability in Dirac semimetals. So, and I'm kind of pushing my time already almost. Oh, wait a second, I started 5 minutes late, so maybe I'm okay. So one of the ideas that has been floating around since pretty much 90s was the possibility of creating some unusual instability in a 2D electron hydrodynamics by transmitting currents through the system. So think of this as a layer of the material sitting here, and you are sending the current through the right end of the system. The other side is grounded. So essentially what you have somewhat asymmetric boundary conditions in the system. And if you analyze the hydrodynamic flow in this system, you will notice that there are some collective modes, in this case plasmons, that are essentially reflected on the left end without amplification. But here on the entrance of the current, the reflection is actually asymmetric. The plasmon coming in with one amplitude and coming out back with larger amplitude. And I'm not going to give you the specific details, but essentially that's the old idea that has been analyzed in 90s by Dyakonov and Schur, and this is called Dyakonov-Schur instability. And if you consider again the solution in the form of plane waves, you will see that some of the waves for a given direction of the flow velocity u0 will develop an instability. The imaginary part will become, for the frequency, will become positive. And this exponent will give you exponentially growing amplitude in time. There are some analytical expression. So what will happen eventually? Well, what will happen, you will be pumping the energy into this plasmon type of mode, bouncing back and forth. And of course, eventually you will reach nonlinear regime, and the system will start emitting waves from the system. So this is the outcome of that proposed experiment. It has not been observed in exactly that form, but there are some indications in the opposite sort of type of setup, when you have the wave sent to the system. Through the absorption of that, you might seem to get an indication that this instability is possible. So this is the old story. Why I'm telling you this? Well, because we actually realized that the analysis that has been done in 90s was done in a non-relativistic hydrodynamics. So basically without the presence of that chirality, without the presence of relativistic-like dispersion relation. So we wanted to reanalyze and see what changes if you have relativistic-like spectrum. And what happens is, one of the things that is very important is the energy conservation relation that becomes very tightly connected to the momentum conservation, simply because for the gapless quasi-particles, the large change in momentum means immediately the large change in the energy. So reanalyzing the system carefully, you will find something more or less expected, in fact, well known, that you will find some collective modes of the same type as you had in non-relativistic spectrum. Basically, those are the plasmons in 3 and 2 dimensions. They have slightly different dispersion relations, but nevertheless, those are plasmon modes. And there is additional mode that is appearing in both 2 and 3 dimensions, and it is driven by the hydrodynamic velocity u0. This is the so-called entropy wave. And here I'm considering the solutions in an infinite system without those boundary conditions yet. So that's basically what we have to start working with instead of just having only plasmons. And the presence of this new mode in an infinite system implies that in a system with the boundary conditions, we actually have a chance also to bounce it back and forth and see if it can potentially be amplified. So we set up the boundary conditions, we consider the corresponding collective modes, and we will find that in the 3-dimensional case in particular, the solution is actually given by this formula, approximately by this analytical formula, where you have some non-zero imaginary part for the collective mode, just the same as for the plasmons. The only difference is the sign, but that is not a big problem because u0 is the flow velocity. We could send the current either in or out, depending on which way we want to set up the system and analyze what happens to it. And of course, that means that we do have 2 types of instabilities. One of them is the plasmon instability. So the plasmon modes are shown in the red. The entropy waves are shown in the blue. And on the right-hand side, I'm showing the imaginary part. Notice that the red line is also having the imaginary part. This imaginary part is non-zero. For the plasmons, it's tiny. For the entropy wave, in fact, it's very large. In fact, it's not surprising since the plasmon modes are gapped and sort of high energy in a sense. The entropy wave mode is gapless and small energies. The imaginary part becomes large, and therefore it implies immediately that the instability will be not only present, but also will be very strong. So this relativistic-like dispersion relation implies that we have not only a new type entropy wave instability, but also extremely volatile instability that could actually develop very rapidly. The same, by the way, analysis extends to 2 dimensions. I'm not going to dwell on the details. The idea is the same. The results are pretty much the same qualitatively. And that basically brings me to my conclusions that in Dirac and Weil semi-metals, we can potentially achieve electron hydrodynamics, and that electron hydrodynamics is very special. It's chiral because it involves chiral degrees of freedom. The topology is pretty much present in that hydrodynamics as well. It's captured by the Chern-Simons currents and densities that not only appear in the equations, but also play sometimes crucial role, giving rise, for example, to new type of collective modes. So those new anomalous hydrodynamics modes are expected in such materials, and the spectrum is very rich, and the details can be found elsewhere. The convection, which is one of the characteristic features of hydrodynamics, seems impossible completely due to the strong Coulomb effects and largely due to impurities in 2 dimensions. Now, of course, if you trace carefully the derivation of these ideas, you will realize that, in fact, it's not very much connected to the fact that this is a chiral hydrodynamics. It's pretty much any electron hydrodynamics will be true, because for the electron hydrodynamics in a material, the compressions and decompressions of electron fluid are very costly energetically. They are screened away very efficiently, and that's essentially what kills convection. Now, because of the unusual features of this relativistic-like hydrodynamics, there could be a new type of entropy wave instability that can develop. And of course, it's a very efficient type of instability, much more than that of the Diakono-Schur type, and therefore it may have very interesting applications. If you create this instability, you could create a source, for example, of terahertz radiation from the system that might be very valuable for applications. And with that, I will essentially stop. I'll just mention briefly that a lot of the details that we learned about these materials covered in the textbook that appeared recently in World Scientific, and it's on sale now. So with that, I'll stop.
Thanks a lot, Igor, for this very nice talk. And we are open to questions. So please unmute yourself and ask questions to Igor, please. I ask one question to you, Igor. So,
okay.
So this entropy wave instability, does it tell us that now we have to do some dissipative kind of hydrodynamics? So does it tell that there should be some kind of uh, bulk viscosities or these kind of things that one has to take into account for
these? Actually, in this analysis, I might have to admit we only included some minor dissipative effects. But the funny thing is that, in fact, viscosity will not be very critical for damping or affecting the entropy wave instability. The reason is very simple. The entropy wave instability is heavily relying on the oscillations of essentially density and entropy. So if you wish, temperature and chemical potential, and almost insensitive to the oscillations of the fluid velocity. And as a result, it implies that that kind of dissipative effect due to viscosity, which is essentially suppressing the fluid flow, will be almost irrelevant. So in fact, it is an extremely important question about the viscous effects because they might be substantial, but fortunately enough for the entropy wave, in view of its nature, it will be almost irrelevant. So in fact, it is the momentum relaxing processes as well that will be sort of not as critical. So provided we have reasonably good electron hydrodynamics, and reasonably good, I mean, realistically what is achieved, LEE, the length of the electron-electron scattering is only about 4 or 5 times smaller than the momentum relaxing length scale. So even in that regime, I think it's pretty much realistic, which, by the way, is not the case for the Diakonov-Schur instability because that is much more sensitive to the oscillations of the fluid velocity. And in fact, for that reason, it's extremely difficult to observe.
And I had another naive question. So there were some discussions that for this Dirac-Weil semimetals, there can be deviations from hydrodynamics. So when is it happening?
There will be.
Okay.
Well, in fact,
what is the criteria for
that? It's the achieving of the hydrodynamics, which is the hardest part. So in fact, almost everything we see so far is deviations. In fact, we cannot guarantee that the hydrodynamics has been even seen in this 3D Weil semimetals. The challenge is that essentially at small temperatures, you need extremely clean samples, first of all, so that you avoid all kinds of momentum relaxing processes. You want to increase the temperature a little bit to actually free up the phase space for the interaction, because you need this strong electron-electron interactions. And when you have the Pauli blocking, it's forbidden. So you have to heat it up moderately at least. But then when you start to heat it up a little bit too much, unclogged processes start to be dominant, and the phonon scatterings with the lattice will become dominant. And in fact, you achieve a diffusive regime instead of hydrodynamic regime. So in fact, it's an extremely delicate balance to achieve hydrodynamics. And almost everywhere you move slightly away from, you are basically breaking it up. So it's very fragile state, and it might be very difficult to achieve.
Thanks. Igor, there's a question from Noriyuki. Noriyuki, please go ahead and ask.
Hi, Igor. Can you hear me?
Hi.
So I have a question.
Hi, yeah, Noriyuki, I could hear you.
Okay, so first of all, is there any signature of chiral magnetic effect, like negative magnetic resistance in this system, like hydro?
Right. Well, negative magnetic resistance has been observed, and in fact, achieving hydro regime is not a necessary criterion for that. Hydro regime is a little bit more special. In fact, negative magnetic resistance will be seen in potentially both in kinetic and hydrodynamic regime. In the kinetic regime, I believe it has been demonstrated experimentally that it is observed by a bunch of experiments, including some of those quoted in the previous talk. So yes, there should be negative magnetic resistance in principle, but again, it's not very, I would say it's not the most signature effect possible for the relativistic-like hydrodynamics.
So you mean the qualitative feature is different from the ordinal Bielefeld in this system if realized? In the sense
qualitatively different. I don't think there is a qualitatively different regime. Essentially, the thing is this, that when you're considering chiral magnetic effect in the form of negative magnetic resistance, you basically have to set up the response of chirality to the magnetic field and the driving electric field. So the driving EB fields, they will generate chirality irrespective of the kinetic or hydrodynamic regime. So it's basically going to happen in both of those regimes.
Yeah.
The momentum relaxing processes are not necessarily killing this process in the kinetic regime, and they are pretty much ignored in the hydrodynamic regime. So qualitative difference may appear, but it doesn't mean that the effect is absent. It will be just a slightly different prefactor in the negative magnetic resistance. So basically, it's not absent there, and I don't think there is anything qualitatively very different. But I mean, this effect by itself is not the most interesting for the hydrodynamics, because it's already present in kinetic theory and basically much easier to achieve than the hydrodynamics itself.
Okay, yeah, I thought it will be interesting if different. So yeah, thanks. So
frankly, I didn't look carefully at all the formulas to tell you the difference in the coefficients, but essentially I do know that essentially all the key features, chirality generation will be there, chirality scattering will be also have to be included, so that if you wish, gamma 5 effect. Now, the only things that will change is essentially the role of the momentum relaxing processes, the scattering on impurities, that will essentially be less important in the hydrodynamic regime.
Yeah, good. Thanks. Okay. So, and other question. So, in this system, is there any chiral magnetic wave?
Well, the chiral magnetic wave is a separate story, but essentially, it's most likely either highly damped or even an over-damped wave. Actually, there are several things. First of all, it's gapped. Secondly, it's very susceptible to the damping due to electrical conductivity. So the electrical conductivity tends to kill the chiral magnetic wave simply because the oscillations of the charge that are necessary to support that wave will be screened out more or less in the same way as I was discussing in the case of the convection. So because of that, it's damped. And in fact, if the coupling is not very strong and if the conductivity is pretty high in the system, it will be over-damped mode.
Okay, thanks. So on the by the way, you found linear propagation mode in this work, in one of your work, right? So even in the absence of chiral magnetic wave, so there are chiral related modes. Yeah, this one. So is this
right? Like... Well, this mode actually has some resemblance to the chiral magnetic wave, but I should also say that here we ignored the effects of the electrical conductivity. In fact, including electrical conductivity will also play against this mode, because again, these oscillations of delta mu will be screened out by the presence of the conductivity. And in fact, this mode may well become overdamped as well. So the effects of dissipative effects on these collective modes is actually is a very tricky issue. It has not been analyzed, at least in our paper, in their full complexity.
I see.
So take this mode with a grain of salt.
Okay. So let me ask final question. So while you consider this in the tabletop experiment, but is this analysis applied to, for example, early universe or proto-neutral star, for example?
Right. Well, some things they do apply. For example, some generic analysis of collective modes, for example, could be more or less easily transferred from solid-state materials to some relativistic system in stars and everything. However, one has to be always very, very careful. We do know about the overall electrical neutralities of these plasmas, and they are achieved in very different ways in those two types of systems. In solid-state materials, you have the rigid ion lattice that is giving you the background, and therefore deviations due to compressions and expansions, they are automatically penalized. In the case of relativistic systems, when you have, for example, some protons that are neutralizing the systems, electron-positron systems, they might be only lagging slightly behind, but not necessarily rigidly fixed in density. So one has to carefully analyze those things. Also, very often in astrophysics or the early universe, you have the electron-positron plasmas that are basically compensated in a sense that you have equal number of electrons and positrons, approximately equal number. And that is, again, a somewhat special regime that has to be analyzed separately. So that is called the Dirac fluid if it forms. And I didn't really analyze it in any detail here. I was pretty much assuming more or less standard plasma dominated by mostly electron quasi-particles. So yes, many ideas, they do transfer, but you have to be kind of very careful because the setting does change and sometimes important physics is modified.
I see. Thank you very much.
Okay.
Are there any further questions for Igor? I don't see any. So thanks, Igor, for this very exciting topic. Generated so many questions, and I'm sure there will be further questions. So we will let you know through the Slack channel, and I will encourage everyone to ask many more questions there. And thanks, Igor, again. And thank you everyone for participating. And so we end this session today, and we meet tomorrow again for the last day of our workshop.
Thanks, Igor. It was a very nice talk.
Okay, thank you. Thank you, Rob. Thank you. I think it was you, right?
Yep, that was me.
I cannot see anything, but I recognize your voice.
Anyway, it was a very nice talk. You clearly spent a lot of work on it. Thanks a lot.
Thank you. Thanks for the invitation.
Take care.
Bye, everybody.
Bye.
I suppose there is nothing else left today, right?
Yeah, so we break it for the day. Yeah. Thank you.
Yep.
Okay. Bye, everybody.
Bye.
Bye.